Okay, so this video is going to be about projectile motion. So in class so far, we have talked about vertical projectile motion. So this is when an object gets thrown straight up in the air. And we know this is just one-dimensional. It has motion just up and then it comes back down. We know that it has an acceleration to it, and that specific acceleration is negative 9.8 meters per second squared. Then, as we'll move in through projectile motion, we will start talking about the horizontal aspect of projectile motion. So this is saying maybe we have this table, object goes off the table. When it leaves the table, it starts to fall down. Why? Mainly because gravity is pulling on it, so there's an acceleration down. But it still has this component of the velocity going to the right. And this component of the velocity doesn't actually change because there's nothing there to change it. Okay, so just to kind of review horizontal projectile motion, and I know we're about to start talking about this in class, but just to kind of review it, we have this object and it's rolling off the table. Maybe it has a velocity of 10 meters per second. It's going really fast, right? This table is 1 meter tall. So as it comes off the table, it's going to follow this parabolic path, and I know it's not exactly a great parabola, but then it's going to hit the floor right there. Okay. Now there's two different aspects of the motion. We have the motion of it falling, which we will show in the green, so it falls down, but it also has the motion of it going forward, which we will show in the blue. Okay. So as it falls, it's going to continue to gain speed, so I'm actually going to decrease this arrow a little bit. Okay, it's going to gain speed as it falls, and this is its acceleration. Okay, but in the horizontal direction, it's not gaining any speed. It's not accelerating. Why is it not accelerating? Well, there's nothing there to push or pull on it. There is no force. There is no fan. There's no gravity. There's nothing that's going to cause it to go forward. So in which case, that means this distance between the table and where it lands is related to that 10 meters per second multiplied by whatever time it takes to fall, right? However long it's in the air. So that's the question. How do we find that time? Well, we can use the fact that this is the vertical component starts off at rest. So we have to say, okay, in the vertical direction, and that's not green. We're going to do this in green. Okay, in the vertical direction, the initial speed is 0 because it's all going off the table to the right. We know that the acceleration is that negative 9.8, it's g, and we know that it falls a distance of 1 meter. So we could actually use x is equal to VOT plus 1/2 AT squared to actually work this out. We know this goes away because the initial velocity is 0. So to solve for t, it would be 2x is equal to AT squared. T squared is equal to 2x divided by a, and then square root it, right? So plugging in the information, we would get t is equal to the square root 2 times a negative 1 meter. Why is it negative 1? Because we're falling down, divided by negative 9.8 meters per second squared. And that's why we have to have the negative in there, because that negative and this negative are going to cancel out with each other. So when you plug it in your calculator, you get 0.45 seconds. Okay, it's 4.5 in a lot of decimal places, but that's what we get. So that means if we come back here, then there's our time that we're going to shove into this equation. Okay, switching back over to blue. That means we have 10 meters per second multiplied by 0.45 seconds, and we get a distance of 4.5 meters. And that's where we would put a marker or something like that to predict where this ball is going to go. Okay, so the bottom line is that when we're dealing with vertical and horizontal, there are certain things that we have to keep separate. The acceleration here is g. the acceleration on the horizontal is 0. There is no acceleration in the horizontal direction. So we have constant acceleration. Here we have constant velocity. Okay, so here a position versus time graph would look like this. Here a position versus time graph would look like that. Okay, and we have to keep those separate because this all of a sudden is the up and down motion while this is the left and right motion. So maybe we don't want to call that x anymore. Maybe we're going to call that y. We're dealing with both motions at the exact same time. So that means if we have this object, maybe a cannonball, that gets shot off and it lands at about the same height that it was shot, okay, then we have some questions. Like maybe we want to know how far is it going to go? What is the distance that it's going to go? This thing is shot off at, say, 45 degrees. And maybe we say it's shot at a velocity of 15 meters per second. Okay. Well, we got two components to our velocity here. We have an x component and we have a y component. That's not what I want to do. We have a y component. There's a part of that velocity because it's going off at 45-degree angles that is in the x and part of it's in the y. And we are going to use sine and cosine. Specifically, this would be 15 times the sine of 45 degrees. This would be 15 times the cosine of 45 degrees. And what you'd actually find out is that these are exactly the same thing because of the fact that it's 45 degrees. So we have 7.88 meters per second. Okay, I'm going to clean up this image a little bit. We have this object that has an x velocity, 7.88 meters per second. It also has an initial y velocity of 7.88 meters per second. This is the general way that we would start any kind of projectile motion problem, is break down the x component, so it's velocity in the x, this is velocity in the y, and they are technically both initial. Okay? In order to find out the distance that this thing travels, we have to know the time that it's in the air, right? Because distance is going to be the velocity in the x direction times the time. Well, in the y direction, we know that we have an acceleration. Okay, I'm going to switch over and do things in red. So that we know that there's an acceleration in the y direction that is the negative 9.8 meters per second squared. So that means we could actually use, notice I'm using y, VOT plus 1/2 a t squared. If we start and end at the same position, okay, we're going to call that y equals 0. This one's y equals 0. That's going to be a 0 in that equation. The initial velocity is 7.88 meters per second times t plus 1/2 times a negative 9.8 times t squared. And plus the 1/2 times a negative 9.8 meters per second t squared. Okay, slightly off screen. That right there is a quadratic equation. Okay, write a little bit better. 0 is equal to 7.88 t plus 1/2 negative 9.8 t squared. That is a quadratic equation. You could plug that into your calculator and find out the roots for that. One of those roots is going to be t is equal to 0. What's the other root? Okay. And it turns out the other root to this one is at 1.61 seconds. Okay, now all I did was stick that in my calculator and figured out where that's 0. I graphed it basically. You could also use the quadratic equation to do it as well. So now that we know that it's only in the air for 1.61 seconds, then we can come back here and say, okay, we know that it's traveling 7.88 meters per second in the x direction, and then it's only in the air in 1.61 seconds. So how far did it go? Well, we do 7.88 times 1.61, and we get that it went 12.69 meters. Okay, so in general projectile motion, we have to deal with things like an angle, we have to deal with things like an initial velocity in the x, an initial velocity in the y, breaking out what's going to happen in each case. So it might be beneficial for us to break apart our given information into what is vertical and what is horizontal. Okay. When you do that, know that in the vertical direction we mainly always use this equation, and in the horizontal direction we usually use that equation. Okay. Now, I know this is a lot of information, but I will see you next time.